Today I've got a problem from Schwarz's quantum field theory in the standard model. I need a bit more practice, so I'll just work on part A of this. Here we're trying to integrate out the A field from the electromagnetism Lagrangian. This is still a classical field theory problem, but it displays a lot of the techniques you still need strong for quantum field theory. I'm going to do this somewhat thoroughly. So instead of just stating the equations of motion straight off the bat, I'm going to first derive the equations of motions. And then from there, I'm going to solve them in momentum space because the final result is looking for is in momentum space, so might as well work there early. And then finally actually do the problem. Okay, so let's do one then. Well, to get the equations of motion, we want to vary the action and look for the stationary points. So the action is the integral over space-time of our Lagrangian density, which is a function of space. And we want to say if we vary our fields, that will vary our action. And we insist that action is unchanged for our solution fields. That is, the variance of the action is going to be this integral over however our Lagrangian is varied when we vary the fields. And we'll also insist that it vanishes at all space-time points, that is locally. What do I mean by that? I mean that this right here, that is still a function of x, and that is going to be the same thing as 0 for all x. Let's get into varying our action. What we're going to vary in our action are actually the field itself and its derivative. I guess we'll call it that. Now, we're not varying space itself, so the variance of the derivative, will actually be allowed to replace it with the derivative of the variance of the field. And you can kind of product rule it out with if you treat this as like an operator and see that this has to be true. Okay, let's get more explicit. Our Lagrangian density, it's going to depend on our electric field strength tensor. And this tensor is given by the well-known form here. So you can see it's antisymmetric in its two indices. If you interchange mu and nu, you get the negative. Okay, so we have those two raised and lowered multiplying each other plus A and J. The variance, or I'm probably using the wrong terminology, but the wrong exact wording. The variance of the Lagrangian density. That's going to be its partial derivative with respect to how it depends on the field. And I'm going to keep things lowered here, times how much the field has changed, plus how much the partial derivative with respect to how much it's depending on the derivative of the field, times how much the derivative of the field has changed. Oh, I actually get to keep that lowered, my bad. And I already said that this we're allowed to bring in here because we're not deforming space-time itself. Let's calculate these two derivatives. Notice that the electric field strength tensor doesn't depend explicitly on the field, the A field itself. It depends on its derivatives, and we're treating the field strength, the field, as if it's independent from its derivative, even though we're doing this kind of weird thing over here. So this partial derivative will just be 0 for the field strength tensor part, and then we're going to have a partial derivative acting on the source term. And as you can see, we're just left with the source. Now let's do this derivative with respect to the derivative of the field. Okay. Looking back at the Lagrangian density, this does not depend on the derivative of the field, but this will. And I always find this index shifting a little annoying here. But let's do it. It's going to be -1/4, and it's going to be our partial derivative acting on our f squared, which is like f raised and lowered. So that means we're going to have what do you call product rule going on. But notice that we can write them both lowered if we explicitly lower the second one with the metric. And then the metric will, of course, commute with this differential operator. So we actually don't need this case, this term, that when we take a derivative of it, it's going to be identical to this one once we remultiply in the metric. So we can really treat it as if it's squared. That's not always the case. There are cases where indices are not as friendly, but it is friendly in this case. Okay. So right here, that is exactly what we're taking a derivative with respect to. Oh, my bad, my apologies. I should write -1/2 f raised 1/2 because we're having it's just the square going down, f raised multiplied by the derivative acting on just f lowered. Anyway, as I was saying, this is exactly what we're taking the derivative with respect to. So we're going to get I'll leave that there. We're going to get for this whole term 1 minus, okay, we have to take a derivative with respect to that one. Now this is something that's escaping me for one moment. I know this isn't that difficult of a derivative there. Well, ugh. Oh, okay, I know. That is the same thing as a Dirac delta. Sorry, not Dirac, Kronecker delta with a mu alpha. Derivative with respect to mu. With respect to alpha. We want to throw a Kronecker delta in here to make this easier. Okay, forgive me. I think doing it correctly with indices would be easier to follow. So I'm going to do that. First of all, doing it correctly with indices means we need to be careful with what we label them. So here we're calling it mu nu. That means when we're squaring here, we have to use a different set of indices. So let's use alpha beta multiplied by f alpha beta. And we're going to do the product rule. Minus 1/4 times our, I'm going to abbreviate that partial derivative, which is a partial f, although just a partial mu nu f alpha beta up front times a derivative f alpha beta. And then we're going to have plus f alpha beta lowered times a derivative f alpha beta raised. My earlier statement about raising and lowering these two commuting with a partial derivative we're considering still holds. So that means we get a factor of 2, and we just have f alpha beta raised times our partial derivative acting on one of them. Now let's rewrite what the field strength tensor is. Okay. Now, This, multiplying that, well, taking a derivative with respect to that, we know we would get 1 if this were exactly partial mu a nu with these indices fixed, no summation implied. And looking at the very left-hand side here, you see there's no summation implied. But we can only get that for that one case. For example, if this were 3 and nu doesn't equal 3, this partial derivative would go to 0. But if it were exactly 3, and we still have mu here, the partial derivative would go to 1. So that means we have a Kronecker delta situation going on. So this term gives you 1 only if alpha is the same thing as mu, and beta is the same thing as nu. A similar thing happens here, except the indices are interchanged. Mu and beta have to be the same, and nu and alpha have to be the same. So overall, we get minus 1/2 f alpha beta times our Kronecker deltas. And you can immediately see how that acts on our field strength tensor. I'll write each term explicitly. So alpha goes to mu, beta goes to nu, minus alpha goes to nu, beta goes to mu. I've already mentioned that the field strength tensor is antisymmetric. So that means this right here is the same thing as negative f mu nu. So we end up getting 2 field strength tensors overall to get negative 1/2. Actually, not negative 1/2, just negative f mu nu. We have both our derivatives. Now we can write out the variation of the action. Okay, we'll start with varying the A field directly. That just gave us the source term times the variation in the field, plus we want the derivative we just calculated times the variation in the derivative of the field, which is the same thing as the derivative of the variation of the field. We would very much like for this derivative to not be acting here, because then we would be able to factor out an overall variation in the field. We may do that by integration by parts. So this term within the integration will consider an overall derivative. I'll just write this schematically. We have an integral, an overall derivative acting on f and a. Our field strength tensor in the field itself, we demand are 0 at infinity for physical reasons. We don't want infinite fields. So the integral of the derivative of the two will just be a boundary term at infinity. And we set that 0. Very good. We can use integration by parts to call this thing then. Well, before we do integration by parts, we look at just the product rule. And within a derivative, that left-hand side is 0, and the right-hand side looks like a partial f plus f partial a And the point is, we get to replace f del variation of a in our case with the negative of variation of a times derivative of f. That was very long-winded. I know you know this. Feel free to skip. Sometimes I like to get a little long-winded because it helps me not miss any details. So we got our variation, and then we have the derivative acting on negative f mu nil. Let's cancel that negative. Let's factorize that variation. Ooh. Did I accidentally? Yes, these should remain raised. Now, we want the variation in the action to equal 0 for all field deformations. That can only happen if this quantity itself is 0, which tells us that our equations of motion are the derivative of our field strength tensor plus the J field are 0. This looks slightly different from the more conventional minus the field. And that's just from how we introduced the Lagrangian at the beginning. Now, part 2. Let's solve for the A field. We're going to do this in momentum space as well. First of all, let's write out our equation of motion in terms of A itself. So that means we have a raised it doesn't matter if things are raised or lowered. Nope, sorry, that's a mistake there. Wait, is it? Oh, my bad. I think I did a slight index error with my final result. Let me eye that. Yes. Yes, I did. Notice that is with a nu, and I factored out with a mu. So over here, let's just relabel that to nu. So that's a J nu, and call it a nu. Very good. Okay, let's simplify this. We get a D'Alembert operator acting on A minus 2 partial derivatives acting on A. This would be very nice if we could rewrite it as a single differential operator acting on a single A. well, we can't do too much with this right hand field because it's getting contracted with one of the derivative operators, but we can do more here. Box a new, we can introduce an a mu like we have here by using the metric as usual. So we can call mu, that's not quite right. Okay, well, first of all, let's put those on the same footing. Okay, I like that form a lot more. And call it new mu, contracting with a mu. The metric is independent of the derivatives. We're dealing in Minkowski space anyway. And it's symmetric, so we can call that mu nu box a mu. So we just rewrote our differential operator as mu nu box a mu plus derivatives acting on a mu equal to negative j. And we can factor this out so that we have our derivative operator looking very slick. And something is wrong here. I feel like I'm missing a negative sign within my derivative operator. Is that accurate? It is. I had it here and I just neglected it here. There we go. Very good. Now let's transform things into momentum space. And actually, before I do that, well, as I do that, I want to point out that this differential operator right here is actually not invertible. That is, if you're trying to solve the equation here for A, for whatever J field you throw, J source, you cannot uniquely determine what the A field is. And this comes from the gauge freedom of the A field. And you can see this show up pretty explicitly as well within momentum space. So let's go there. We'll use Peskin and Schroeder's definitions for conventions for the derivative, the Fourier transform. So for example, Fourier transform of fk, that's the same thing as that's a derivative. Oh, what am I saying? Derivative. That's the spatial integral with a plus I k contracted with x, f of x. And then the function of x is the same thing as d to the 4k integral over momentum space divided by the 2 pi's with a negative sign between their contraction. And we're using the mostly minuses signature. I'm saying all this so that justify Fourier transforming derivatives into negative ik mu's. You can figure that out pretty easily with another integration by parts, which story for earlier, I'm sure you're familiar. Okay, so box That is two derivative operators contracted, so that gets to negative I squared. K's contracted with each other, so that becomes a negative k squared. And then the two derivatives, they get set to negative I squared k nu. So our equation of motion gets mapped to negative k squared metric plus now k mu, k nu, our A field now, I believe I kept it with mu, yeah. Now the Fourier transform, so it depends on k, equaling the Fourier transform of our source field. Let's prove real quick, I like this little check, that our derivative operator here, let's call it d, is not invertible. Let's show that. Our approach is to show that its kernel is not trivial. So we want to show that its kernel is not just the zero vector, because if that is true, when solving this equation for even just kernel, well, even just d of a field equals 0, there are multiple solutions, so it's not invertible. And that also translates into the specific case where we have a field it equals not invertible. And the easy way to show that is consider it acting on k, act on the vector or the momentum itself. So we have d mu nu acting on k mu. This guy and this guy, they contract to give you k squared. And then this guy and this guy just give you k with nu raised. So we have negative k squared k mu raised plus k squared k mu raised, which is 0. And we've shown that the kernel of d is non-trivial, so d is not invertible. How do we deal with this? I know there are more sophisticated ways to deal with gauge fixing and all that, but I'm going to just pick Coulomb gauge, not Coulomb gauge, Lorentz gauge. When we pick this gauge, this differential operator is now invertible. It removes extra freedom of that kernel subspace. Okay, very good, very good. Well, let's translate that to momentum space real quick. So if k is contracted with its with the Fourier transformed field, we get 0. That will be handy later. Okay, now we're going to solve our equation of motion that we've derived up there for A. Okay, yeah, actually this is not difficult at all now. Now that we've picked a gauge, notice we're going to be contracting our Fourier transformed field with a k-vector. So this right term will give us 0. So that means we have negative k squared metric acting on A equaling negative j. Cancel the negatives, contract with the metric, and divide with k squared. And we have our solution in Fourier space. Okay. Now let's solve the original problem. We want to state the Lagrangian in momentum space and show it has a term, as I said, a term like j contracted with j over k squared once we plug in the equations of motion. To do that, let's consider the definition of our action again. Now, these are all functions of x in here. We want to have things in momentum space. So I'm going to use the Fourier transformed field to represent each of these. I'll use a momentum p, actually I'll use momentum k for these ones and a momentum p for these ones, so that we can rewrite our whole action as an integral including over momenta. Minus 1/4. Now it's the field strength tensor Fourier transformed of k, the same but on p, so on. Oh, and don't forget we're multiplying. Ooh. I'm forgetting my conventions right here. It won't affect the final result, but I'll feel bad. Nope, it is a negative. Okay. Now the only thing in our whole expression that depends on x are these exponentials. If we commute this past the momentum integrals, we can find that integral, and we'll have something like an integral for x times an exponential of negative ix k plus p, and that goes to 2 pi to the 4th Dirac delta of k plus p. And rather than keeping around both k and p momenta now that we have this Dirac delta, which will enforce p, well, let's say k is negative p, let's collapse the x and p the x and k integrals. So we're just left with an integral over p minus 1/4 f mu nu. Instead of k, we have now negative p. And now this won't matter. I'll keep that as negative p. Now we want to insert our solution for A into our Lagrangian. Our solution is stated in momentum space, so I stated our Lagrangian in momentum space. To do that, let's write out those field strength. Let's figure out what that field strength product looks like explicitly. Let's choose another color. That will give us a, well, that was a negative I from the derivatives popping out. And we'll pick up another negative because this is, oh no, I'll keep it explicit. So just writing out this factor first, we'll have negative p mu a nu negative p minus negative p nu a mu negative p. Now let's write it in the second factor. I'll again have the negative I from the Fourier transform, and that will be a p mu a nu of p. For the dependence on p though, I won't write that explicitly. I'll just write it out for the negative dependence. Let's do this product out. Let's factor out the sign from the negative p. So overall we'll have a negative I squared p mu a u negative b and that will go out to plus okay, do it term by term. We'll have a p squared, and then we'll have a contraction between the negative p and the positive p transform fields, and then we'll subtract off contraction between p and positive field, then p and the negative field. We'll get a second of those terms. And finally, we'll end up with another for p squared contraction between the negative and positive fields. So we end up with some terms matching. So we have a factor of 2 out front. P squared, a negative, a positive, minus 2 p dot a positive, p dot a negative. And in fact, you could pull the negative here inside there if you wish. Okay, we're getting very close. Before we go farther, I'm going to point out, right here we have a contraction between the momentum and its the Fourier transform field. And we know from our gauge fixing Lorentz gauge, that is 0. So I'm going to enforce that here, so that our result here is 2p squared, negative field contracted with a positive field. This means we get to write our action now as we have the minus 1/4 factor, so we'll have a minus 1/2 factor, p squared, a field, negative p, a field, positive p, plus a field, negative p, dotted with the j field, positive p. Our solution was a field equals 1 over p squared j. Well, I should include indices now. Okay, so let's substitute this in, and a little note, p squared, of course, is the same thing as negative p squared. So s is integral of minus 1/2 p squared 1 over p squared j, sorry, contracted, j negative p contracted with 1 over p squared positive field, adding on negative field j times its positive version. One factor of 1 over p squared drops, and forgive me, I forgot to include the 1 over p squared here. Overall, we are left with one half 1 over p squared negative Fourier field contracted with positive Fourier transformed field. So that means our Lagrangian density and momentum space is 1/2 1 over p squared j source negative p j source p, and that matches the solution form we wished. Oh, you see why I only did part A. I need to do a bit more practice, but highly recommend do some QFT. It's good for the soul. It's very cool. See you around.